going to look at Euler's formula. Before we do though, we talk about these things called Maclaurin series. What it does, it's a series, but it represents a function as some infinite sum. And what it allows us to do is basically turn any function into a polynomial. Here's the one for the exponential. So e to the power of x can actually be done by this. Summing up all these terms, so the pattern is x to the power of n over n factorial. So 1 plus x squared on 2 factorial, and so on, and so on, and so on. That infinite sum would be equivalent to the function e to the power of x. Here's a picture. Right? So obviously the black one here is e to the power of x. The blue one that I drew in is just those 4 terms. So you see it doesn't fit perfectly at this stage. But what you'll find is if you jumped onto Desmos and had these two, which is where basically I drew this anyway, but then started adding more terms, you'll see that blue one start wrapping around the exponential function. And if it was possible to add in an infinite number, it would fit perfectly. So it's a really good approximation actually when you're close to 0. That's where it starts fitting, is around 0, and then it sort of moves out, if you get what I mean. So there's e to the power of x. Cosine is all the even powers, but also they alternate plus minus. So you go 1 minus x squared on 2 factorial plus x to the power of 4 on 4 factorial, and so on. So here's a picture of that one. Again, the black one's cosine x. The blue one I just put in those 4 terms. What ends up happening is as you add more terms in, you're changing the degree of the polynomial, so you get more turning points, and that's how it starts wrapping around the sine curve, that you get more turning points and so on and so on. And sine is all the odd powers, but again alternating. And there's a picture of that one. So sine and the blue one wrapping around. That brings us to Euler's formula. Beautiful thing about it now is we can convert between trig functions and exponential functions via this formula using imaginary numbers. So if I let x equals theta into those expansions we just saw, cos theta becomes 1 minus theta squared on 2 factorial plus theta to the power of 4 on 4 factorial, and so on, and sine theta becomes the other one. Okay, so there's the 2. But now in the exponential, I'll let x equal I theta. And if I sub that into our series, look what happens. We get 1 plus I theta. The next one, I theta squared, but of course we know I squared is negative 1. And then I cubed will become negative I to the power of 4. We get that alternating. If I now group these, I get the expansion for cos theta plus I times the expansion for sine theta. And so there's our conversion. We can turn our trig functions, cos theta plus I sine theta, into an exponential function, e to the power of I theta. So that's the formula. E to the power of I theta is equal to cos theta plus I sine theta. And that will be true for all values of theta. Well, assuming theta is a real number, I guess. Which now means we've got another way of representing complex numbers. Okay, we started off saying it was x plus iy. That's what we called the Cartesian form. We then introduced the mod arg form, so cos theta plus I sine theta, and some modulus out the front. That's also known as polar form. Okay, so mod arg form's probably what we more commonly call it, but if you ever hear them say, oh, put it in polar form, they're really meaning mod arg form. Now we have this new way. We can change that cos theta plus I sine theta into e to the power of I theta. Again, we can multiply by the modulus. And that's what we call exponential form. And actually, any time we're using mod arg form, it actually can be a lot more convenient to have it in exponential form. So 4 minus 4i in exponential form, you might even recognise it as an example we did right at the start. And we found out that in mod arg form it became 4 root 2 cos of minus pi on 4 plus I sine pi on 4. Well, now we can write it as 4 root 2 e to the power of minus I pi on 4. It also gets rid of this problem of, oh, do I write cis or do I write cos plus I sine? I don't have to worry about that. Now I'll just go e to the power of, there's the modulus out the front, 4 root 2, there's the argument, minus pi on 4. Now we can use it, of course, for multiplication and division quite nicely. We've got these two complex numbers, root 3 plus I and 1 minus root 3i. If I wanted to find z times w, if I put them in exponential form rather than mod arg form, it would be like this. And all I'm really using now is basic algebra, because we know that when I multiply these, well, I add the powers. We're adding the arguments. We know that. Multiplying, we add the arguments. There it is. So I end up with 4e to the power of I pi on 6. If I want to know what that number is, all right, now I'll move it back into mod arg form and do the conversion. It's 2 root 3 minus 2i. Z divided by w. So again, let's do it that way. Division, we subtract the powers. Well, we subtract the arguments. We're really doing the same thing as when it was in mod arg form. So I get e to the power of I pi on 2. The beauty of that is when I see the argument is just pi on 2, I don't even have to worry about going into mod arg form. I know, well, okay, that's a purely imaginary number. It's I. Z to the power of 5. Well, I'm still using de Moivre's theorem, but I'm using it on exponential form rather than the mod arg form. So the modulus is to the power of 5, whereas I multiply the argument, because if you think about it, the exponential to the power, what do? We multiply the powers. It's exactly what we got. So we got 5i pi on 6, so 32 outside of our minus root 3 on 2, I plus I on 2, we get our answer. Here's a question from, what's that, 3 years ago now. They've given us a complex number and they've pointed out, hey, it's in exponential form. We want to show that this new complex number w, which is z squared minus 1 on z squared plus 1, turns out to be a purely imaginary number. Okay, well, they gave us that, so let's substitute it in. I want to show this is purely imaginary. So what I do is this. I divide everything by e to the I theta and come up with this expression. Because look at what you now have. Those arguments are the negative of each other. In other words, they're conjugates. If I subtract conjugates, I'll get twice the imaginary part, but of course times I as well. And when I add the conjugates, I get twice the real part. So cos theta. That's I tan theta. That's got to be purely imaginary, because tan theta is just a number. I mean, it'll have some value. So I'm saying, say some number times I, well, that's purely imaginary. There's the answer. So there's just a start at looking at Eulers.